yesterday, we looked at the diagram for case 2 and compared it to the diagram in case 1. So we wrote the code for case 1 where the node to be removed is a leaf. And that was relatively straightforward because we could just tell its parent that that child is now null. Case 2 is a little bit more involved, where the node to be removed is not a leaf. It has exactly one child. And so this is a little bit more complicated because now we can't just tell the parent to make this child null. We have to tell the parent that it has a new child, which is the one and only child of the node to be removed. So we're going to need to, in our algorithm here, previously, we just kept track of the node to be removed as we iterated through the tree, and we kept a reference to the parent. We still need to do that. And we also now need a variable to refer to the child that will be rerouted. Okay. So that's where we're headed. All right. Oops, let's not get ahead of ourselves. Okay, so we're going to code case 2 today. And so the first thing we want to capture here in case 2 is, I feel like I missed something. No, this is good. The first thing we want to capture here in case 2 is we're going to do so this was if to be removed dot left equals null and to be removed dot right equals null. Like just to review, it's been a little while. We've already found the node to be removed and we've already have a reference to its parent. Okay. So case 2 is actually going to be an else if that builds on this if statement. And we're going to say else if to be removed dot left equals null or to be removed dot right equals null. So if either the left or the right child of the node to be removed is null, that means we have exactly one child. If both were null, this would have been true, and that's case 1, and this code here would have already run. So here in this block, we know we have exactly one node, exactly one child of the node to be removed. All right, so as I referred, we need a new variable, which we're going to call new child, meaning it's the new child of the parent. And we're going to need to have some conditions here to determine how to initialize the new child. The new child is either going to be the left or the right child of the node to be removed, right? We don't know. We need to determine here's the node to be removed. If it has a left child, that's the new child. If it has a right child, that would be the new child. So we just need to determine which one it is. So we're going to write some if statements. It's very similar to what we've done before. If to be removed dot left equals null, let's write that differently. Let's say not equals null. I think that's more clear. If to be removed dot left is not equal to null, then the new child is that node, to be removed dot left. Else, the new child is to be removed dot right. So now we've successfully initialized our variable new child, and we know if it's the left or the right of the node to be removed. Now all that's required is to relink this new child to the parent. So similar to what we wrote here, but we're relinking it. We're not setting it to null. We do still need to handle the condition that what if the node to be removed is the root? Then that's going to require some changes. So if parent equals null, which means the node to be removed is the root, then the new child becomes the new root. So that's like our boundary condition. Else, if now we need to determine is the node to be removed the left or the right child of its parent. So just like we wrote before, if parent.left equals to be removed, And we had that great question yesterday where why do we use the equality operator here and not compare to or dot equals? And that's because we're actually checking if we're referring to the exact same object, the exact same node in this case. So if the node to be removed is the left child of its parent, parent dot left will now equal new child. Else parent dot right will equal new child. Must have been that one. And we'll just say return. We're done. We did it. All right. So since we noticed that case one and case two are nearly the same, we're going to generalize our code to cover both cases at once. And so I'm going to change this comment to say case one and two. And then we're going to update this code to cover both cases. So all of this, in a moment, I'm going to delete all of this, but I'm going to leave it here for reference right now because I might want to double check to make sure I've preserved all the functionality. But this will become the new if statement. If to be removed at left equals null or right equals null, or they both could be null and that condition will still be true, that's great. So let's initialize new child to null. Okay. So by default, the new child of the parent of the node to be removed, I know that's a lot, will be null, but perhaps we'll, actually, I don't know if we even need this. Let's just leave it like, I think this is more clear. Let's say null. So by default, it's null. If the node to be removed has a left child, then we'll change new child to be the left one. Otherwise, we'll change new child to be the right one. You might notice this is an else, not an else if, but to be removed at right might just be null. So we're just going to be assigning null anyway. So that's okay. But maybe for, this is a complicated algorithm that's hard to understand. So maybe it's worth saying something like this. Oops, whoa, don't know how I did that. There we go. So this isn't strictly needed, but I think it does add clarity to our intentions. So when this code finishes running, new child will either still be null because the node to be removed is a leaf, or it will refer to the appropriate, the one and only child that the node to be removed has. The rest of this code, as pointed out, we don't need to change because if new child's null, this highlighted code is exactly like this highlighted code. We've got it all covered. So now I'm comfortable deleting case one. And honestly, we didn't have to make any changes to case two. I just felt like adding null here and making this an else if added clarity. The code we had written for case two would have worked for case one unmodified. Okay. So there we are. Case one and case two. Love it. We have one more case. Here we go. Case three. As you can imagine, case three is when the node to be removed has a left child and a right child. And when that's the case, it's a bit harder. What we need to do is we need to find another node that we can put here in the tree, right? We're going to be like swapping some other node with that node such that our binary search tree is still a valid binary search tree. There are two ways to do this. I'm going to tell you one, and then I'm going to ask you what the other one is here in a moment. One way we can do this is we can look in the right subtree and we can find the least value node in the right subtree. Okay. I don't think smallest is really the right descriptor here, but we can find the least valued node in the right subtree. And the way we do that is we look in our right subtree and we just keep going left because this node is less than this node because it's the left child. And this node is less than this node because it's the left child. And when we get to a node that has no left child, we know that we have found the least valued child in the right subtree. Okay. And then when we do that, this node can go up here to replace the node to be removed. And if it does have a right child, we'll just link this one in like that. Oh, all right. So here's my challenging question for all of you. I shared one way we could do this. Talk with your partners again for what is another way, another approach to the same algorithm that we could do to swap a node. What do we think? How else could we solve this? Absolutely. We could look at the left subtree and we could keep going right until we get to a node that has no right child. And then we will have found the node that is has the greatest valued node in the left subtree, which would also be appropriate to replace with a node to be removed. Both of those approaches are equally good. Well, we want to get rid of this node, but we have these two children. And so in the previous cases, we only had one or no children. So we could just like put the child there and that makes a valid tree. But here, like we can't like put either one of these here because we would lose the other child, right? So we need to somehow restructure our tree so it's still a valid binary search tree where all the nodes are in the right places, but we got to get rid of that one. So we're basically like we're rebuilding the tree in the least invasive way possible, which is to find like a single node we can just swap up there. Yeah, because when we find the smallest child in the right subtree and put it here, that means that all of these nodes are still smaller than it, or else it would have been over here, right? And all of these nodes are greater than it, or else it wouldn't have been the smallest child in the subtree. So that's why we know it's okay to put there. We know that the smallest child in the right subtree is greater than the node to be removed. And we know that all of the nodes in the left subtree are less than the node to be removed. So therefore, there's some mathematical property for this. What is that? I don't know. Is that transitive property? Come on, math geeks, help me out. No. Via some mathematical property, therefore, we know that this node must be greater than all of these. Yeah. Regardless of my not knowing the right terminology, does that make sense? Okay. All right. Well, let's see what the code looks like for this. The diagram is harder than the code, in my opinion, as is usually the case for the algorithms we're doing. All right. So there's case one and case two. So we're going to add case three. So if our code even makes it here, or if the flow of execution makes it here, neither subtree of the node to be removed is empty. This is case 3. So we have to do some extra work. Step 1, we're going to find the least element of the right subtree. It would be completely valid to find the greatest element of the left subtree, as we said. We're going to find the least element of the right subtree. In addition, that's actually not sufficient. Yes, we need to find this node here, but we also need to know who his parent is, like this parent. So we need the parent of the least node because we have to reroute the link. So we need a couple different variables here. Let's have the least parent, that is the parent node of the least node of the right subtree. And we're going to set that to be removed because the parent, the least node of the right subtree could be this node right here if it has no left descendants, right? No left child. So it could be this. So like we're going to start by saying node to be removed as the parent, and we'll keep updating that as we work our way down the tree. So we're going to initialize the least node to be removed.right because we're going to do the right subtree. And then we're going to keep iterating to the left child until there is no left child. So while least.left is not equal to null, then we're not there yet. There is a element that is less than the others in the tree. So least, we need to update least parent before we forget. Least parent is going to equal least. Least equals least dot left. We've written lots of algorithms with this, right? Where we're keeping track of two different things, like the thing that came before and the thing that is now. In this case, it's the parent and the node. So we always have to update the parent before we change the value and lose track of who the parent is by saying least equals least dot left. When this loop finishes, least refers to the least child of the right subtree. Yay, we did it. We could swap the nodes. So we could take this least node and change its left and right instance variables to refer to this node and this node, respectively. It's a little bit more straightforward to actually just swap the data. So we're going to leave the node to be removed. We're actually not going to remove it. We're just going to go in and change the data of this node to the data in this node, because left and right are already correct, and it just saves us from having to like clean that up. It saves us from having to update the parent. Like it's so many less references we have to clean up. So we're going to take a little bit of a shortcut, which will make our lives a lot easier, and we're much more likely to get this right. We're going to say to be removed.data equals least.data. That's all it takes to actually swap the nodes, because we don't have to update the parent and know if it's left or right. We don't have to update the nodes left and right child. This is all we have to do. The final step, though, is we do have to reroute this link here. So the parent of the least node is still referring to the least node. So we don't have a tree anymore. We actually have an arrow that goes back up here. So that's not a tree. That's what's called like a directed graph. So we don't want that. We want a tree. So we're going to fix that link to whatever this child is. So let's do that. We're going to say if least parent equals to be removed, because this is our special case. If the least parent is to be removed, like pretend this is the node, that's the least one, and so therefore this is the parent. If the node that we're removing is the parent of the least node, then the least node is the right child. Otherwise, the least node has to be a left child. So we do have a special case here to handle that. So we'll say, oops, we'll say least parent dot right equals least dot right. We always know it's least dot right because there is no least dot left, or else it wouldn't be the least. Else, in the more normal case, least parent dot left equals least dot left. Oof, goodness. Yes. It is. We wrote, you'll need to grab the code for case 1 and 2, which we changed at the start, and this is case 3.